let's go to the next topic, which is, so what I want to do next is, and so that's how we would approach these steady vortex rings, or these are rigidly translating vortex rings. The next topic I want to consider is, say, non-steady or non-rigid. And so, so these are solutions of the axisymmetric order without swirl. Okay, let's write it. In the half plane, we have these equations, and u dot normal is 0 on the boundary of H. Such that the vorticity is concentrated. For all t around, or say near a ring around the z-axis. And so when I say vortices here, I mean the 3D. The 3D vorticity. And so in the half plane, that means, so if I have the half plane H, here's R and here's Z, and here's a little vortex. Then in 3D, that would correspond to a ring in 3D. And so, so again, I'm basically looking at point vortices, but now in this half plane who in fact correspond to things in 3D. Okay, so this means so in fact, in the half plane, omega of R and Z and T is like a delta function with some coefficient gamma at some point R of T and Z of T for all T in 0 T. This is what I want. And so is there another chat? Oh, okay. Okay, and so this is what I want. And so really this is I'll study it for initial data that looks like this, and then I'll ask at later times, does this still hold? So we'll, in practice, we'll say omega is like some gamma, a delta function is some R naught and Z naught, and study the evolution. Okay, and there's going to be very little time in the theorems. In fact, this is almost we'll see that the evolution is kind of trivial, and we can prove nice results rather. What we'll do, in fact, is we'll rely very heavily on conserved quantities. And so let me make a simplification I'll always do, which is that I'll always assume let's see. And so also let's recall. Well, so I'll always assume that you know, I have some initial vorticity, and I want it to be concentrated. And up here I have a few parameters. I have a gamma, the vorticity strength, and I have a R naught and a Z naught. Let me just assume for simplicity that gamma is 1, and that R naught is 1, and Z naught is 0. Okay, and so gamma 1, these are all just normalizations. If I can understand this, I can understand anything else. It's not a, and maybe epsilon would be the, I might initially consider vorticity concentrated in a ball radius epsilon around, or on a, say on anywhere on an epsilon scale around this point, RZ is 0, 1. Okay, and so, and the point is somehow this lane scale R from the vertical axis will appear in all estimates, and so it's just easier to imagine I'm considering things on a lane scale of 1 from the vertical axis. It means it saves us some calculus headaches. Okay, and so here's the proposition that I want to prove. Let's start stating this. It has a moderately long statement, but and so we'll also and so okay, and so we're going to rely again on these conserved quantities for the flow, and those include the integral of the vorticity and the integral of the vorticity times R squared. And if I have this situation in mind, then, well, I'll assume that the integral of omega is 1, and the integral of omega R squared is 1. And so this would be true, you know, for my initial vorticity, and then these will be preserved at later times. And I may also assume that say and so I have in mind vorticity concentrated on an epsilon scale. Like for example, I might just consider the ball radius epsilon around the point 1, 0, and that will certainly satisfy this. That'll have this property. And so these are the kinds of things I want to have for the initial data I'd like to consider, and these are just normalizations, really. Okay, good. And so, so the first, and so let's see. We can see actually the existence theorem we just discussed says that I can produce vortex rings by maximizing the energy subject to exactly these constraints, right? And so the proposition I'm about to say, what did I call the proposition or theorem? I don't know. It's called the proposition. The proposition I'm about to state says that if we consider any distribution of vorticity whose energy is close to maximal, given these constraints, then in fact it's got to be pretty concentrated. It's actually got to be pretty concentrated near a point distance 1 from the vertical axis. Okay, so here's the proposition. And let me just, because there's, when I state this and prove this, I'm going to, so here time doesn't play a role, the t variable doesn't play a role. And so I don't really need the superscript 0. And I don't really need the epsilon either. I'll just remember it's there. So for notational simplicity, I should have added 0 here. For notational simplicity, I'll just write it like this. And so, of course, later on, I'll apply it to some solution of Euler, but this is just a, so time plays no role here. It's just a role, kind of a concentration of it. Okay, so assume that omega is a function from the half plane, a non-negative function. It occurred to me today, I've never bothered to mention measurable. Everything's always measurable in this semester. And assume that, and so here's the key point, and assume, and again, we know from the previous theorem where I've stated without proof, we know that if I maximize the energy subject to these constraints, well, the maximizer exists if epsilon is small enough. And so the energy is bounded above. We can construct examples for which the energy scale is like 1/2 log epsilon. We'll see why this is true. And so let's assume that the energy of omega is bigger than 1/2 log epsilon minus some constant, let's call it kappa, say. And the conclusion is that then there exists a constant such that for every epsilon and every, I guess, r between 1 and maybe 1 over epsilon. Such that I guess I can't, I need some, I can't let r be too close to 1, such that a constant times 1 plus lambda over 1 plus r, I don't know, I'm writing it this way, is less than 1 over c. Okay, so this is not a big, this is just a technical assumption. That's not, so r can't be too close to 1. We don't care about that. We want r to be something like, r will be something like 1 over the square root of epsilon in our applications. Okay, for every epsilon and for every r, if the above assumption is satisfied, there exists a point, say, r star and z star in the half plane H, such that r star is close to 1, so I'm at about a distance 1 from the vertical axis, and the vorticity is quite concentrated around the point r star z star. So 1 minus r star squared is less than a constant times this 1 plus lambda over log of r, and the integral over ball of radius r times epsilon of the vorticity. Let me write it like this, is at least 1 minus some constant 1 plus lambda over log r, where sometimes I'll write x for the point r, z, and dx is dr, d Z, just for to keep the notation not too bad. Okay, so this is the theorem, the proposition. And this tells us a lot about the solutions of Euler with the kind of initial data I've described. And so for that data, condition star will hold. And the conclusion is that, well, this says that, and so let me take R to be, for example, epsilon to the -1/2. If epsilon is small enough, then this technical condition will be satisfied. So I just want to, so basically I'd like to take R, I'd like to imagine a sequence with epsilon going to 0, and I'd like to take an R who's diverging. And then this technical condition will always be satisfied. Okay, so R, for example, is epsilon to the -1/2. Then what happens? So this is a small ball. This is a ball of radius squared of epsilon. And this says that, and this log R is of order log 1 of epsilon, a rather large number. And so this says that all but 1 over log epsilon, basically, constant over log epsilon, of the vorticity is concentrated in a ball of radius squared of 1/2 around this point, Vr of x star. Okay, and so the vortex is quite concentrated, and this is a star here. Star is kind of invisible, but and it's concentrated at a point the right distance from the axis. And so this is a very strong, if you like, a kind of an orbital stability property. It says that these conserved quantities force initial data with the property of being concentrated around the axis and having energy kind of big. And so again, the key assumption is this one, which says, so heuristically it says the energy is close to maximal. And the conclusion is then that the vorticity must be concentrated, and it must be concentrated around a point sort of far from the axis. And so what this is going to let us do, we can see right away, is that if I then solve the equation with initial data satisfying hypotheses star and satisfying this energy bound, well, all that stuff is preserved by the flow. And so at every subsequent time, the solution will be concentrated around a point kind of close to the to this line where R is equal to 1. And all it can do is move up and down. And so once I know this, all I have to do is to figure out how is it moving in the vertical direction, and that will be a rather straightforward computation. Okay, and so this, we'll see, this is a lot easier, this lemma, this proposition, than the construction of vortex rings. And in some way it gives us more information. It doesn't just give us one solution. It says that anything whose data is concentrated around a ring in the right way, not just a maximizer, but things who are close to maximizers, will have the same dynamical behavior. They're forced to by conservation, by conserved quantities. Okay, good. So that's the plan. And this will also be useful later on. When we were doing this variational problem early on, the co-rotating vortices in R2, one of the steps was showing the compact support within this set where we wanted to minimize the vortices, and we can find it to live in a certain set. And we wanted to show that, in fact, the maximizer had compact support within that set. And at some point in that argument, we used what I called a vorticity concentration, which was easier in that saying, but it had the same character. So that if the energy is close to maximal, then the vorticity got to be kind of concentrated. And so this is a more complicated version of the same proof. Okay, let's get started with the proof. And it's just calculus. It's hard to attach much intuition to it at places, so we'll do what we can. Okay, so my first goal, we'll start the proof. So the goal, one is to relate the energy E to a more transparent energy. And so let me start by saying, so what is E? And so here I'm going to, so it's this thing we had up here. And here I'm going to write it in this form with, I'll include the RR prime in there. And I'll bring this out there. Okay, so my real task is going to be to understand what this thing looks like as modified here. And so, right, and so I really want a, okay, so there's a factor of pi. I'll bring that inside here. And so I want to look at, so we'll consider pi times this G axisymmetric of R, Z, R prime, Z prime. And so this is as modified by inclusion of this term. Okay, and so that is pi, I guess, times the integral from 0 to 2 pi, and then it was, well, let me write it, cosine alpha, and then here there was a square root of some stuff, and the stuff was, and let's say x prime is r prime, z prime, and so the stuff was x minus x prime squared, and so I could if I would, r minus r prime squared plus z minus z prime squared, and then I have I've included this, and so I could bring that in, and there was a what was it? It was a plus, I think there's a 2r prime, and then there was a 1 minus cosine alpha, if I'm not mistaken, d alpha. And so I can bring this inside here. It gets rid of these things. And then it puts r prime there. And let me call this and there was a 4 pi also in the denominator. And somehow I have a factor of I think there's a factor of 2 here. Right, I have a factor of 2. Let me not worry about where it comes from. So I'll track it down later. Okay, and so then let's just cancel these. We get a 1/2. And I'll call this cos alpha over, say, a plus 2, 1 minus cos alpha to the 1/2, where a is this. Okay, and then I can get rid of this 1/2 and get rid of this 2 because it's doing the same thing in the interval from 0 to pi and pi to 2 pi. Okay, I'd like to then do what I can with this, and so yesterday I stated a result about describing the asymptotic behavior of this function g, this Green's function, as r prime approaches z prime, as x approaches x prime, as r z approaches r prime. Okay, and here I'm doing something a bit general, and so that was a result that was valid as the distance gets close. Here I want something who's valid for all. I want an approximation of this function who's valid for all distances between x and x prime. And I also right. Also, I've done this. I've sort of built this scale. I have the scale 1 in mind, where 1 is the distance of r from the axis, and so that's why this will be a bit different from the general thing I said yesterday. Okay. Anyway, so I can write this. This is cosine alpha, and if I'm correct, this is a plus 2 and no, so 2 times 1 minus cosine alpha should be sine squared alpha over. Okay, I've written this. Let's see if it's right. Is that right? 1 minus cosine alpha is I think this is 4. Someone correct me if I'm wrong. Okay, good. And so what I'll do now is I'll just split this into 2 pieces. I would be happy if the numerator were cosine of alpha over 2, because then I could do a substitution. I could say, t is sine of alpha over 2, etc. And so let's just do that. And then I'll have a piece that looks like cos alpha minus cosine alpha over 2 divided by the same quantity. Okay, and then, okay, without going into details, the first one we see we can integrate. I substitute t is sine of alpha over 2, and then in the numerator I get a dt. And then, so I'll get 1 plus t plus 4t squared to the 1/2. I can figure that out somehow or look it up. And what I get in the end is, for this, we have log of 2 plus a plus 4 to the 1/2 over square root of a. And a, again, is this ratio x minus x prime squared over r prime. And then the second part I kind of is bounded because what? Well, cosine. So I can see that the denominator is dangerous only. Right. So here I'm going from. Let's see. Right. Yeah. Okay. So if alpha ranges from 0 to pi, then alpha over 2 ranges from 0 to pi over 2. That's dangerous only when alpha is 0. The denominator, so I only need to worry about alpha equals 0. And I look at this expression, and then I can see that both cosine alpha and cosine alpha squared are equal to 1 plus order alpha squared near alpha equal to 0. And so in the numerator, I have something of order alpha squared as alpha goes to 0. And the denominator, I have something like a plus alpha squared to the 1/2. And so I can see the whole integrand is bounded, and the whole thing is ordered. Okay, good. And so, so that's that. And then continuing, log of, so I want to simplify this if I can. 2 plus let's see. What do I want? I want to assume if hold on. Yeah, this Okay, this is true because the square root of a plus 4 is bigger than 2. And so this is log of 2 plus, and now let me introduce some new notation. Let's say b is x minus x prime, or x and x prime are rz and rz prime again. And so then a is x minus x prime squared over r prime. And so, well, okay, so we have log of, so the whole thing has a square root. I can take that outside. And then I'll have log of a plus 2 over 4a. So that's a plus 4 over a. So that's 1 plus 4 over a. And 4 over a I rewrite as 4r prime. Over b squared. Okay, and so now I'd like to so okay, so here's the point. Unfortunately, we're out of time, but so what I want is I'd like to see this energy. I'd like to see things in the energy who look like one. So b is the distance between x, rz, and x prime, and I'd like to see things who look like log of 1 over b, 1 over the distance in the energy, because that's how these energies should behave on small scales. Okay, and so I'm making progress, right? Here's something who blows up like. So as b goes to 0, this 1 over b is going to be the dominant term. And so I'm going to just mess around a bit, and then eventually I get something involving log of 1 over b and error terms. And that, I'll be happy with that. And so that will give me an energy who looks more recognizably like the Green's function, like the corresponding energy on the plane. And then I can, and my assumptions will give me lower bounds on that quantity. And so we'll resume this on Monday. Okay, any questions about anything? So this proof is basically just undergraduate level calculus, but it's and this is due to a paper. This is from a paper of Benedetto Cagliotti and Marchioro from around 2002, and the proof there is pretty unreadable, and so the one I'm presenting isn't that fun, but at least it's easier to digest than their argument. Excuse me if any of the authors are streaming this lecture.